Was that okay, or? Okay, so the first one on there, that limit, that slope of the tangent line thing, I mean, that's as easy as it's ever going to get in this class. And so on a test, that's not the level of the problem you're going to have. It's going to be harder than that, but it's because of time. I can't sit here and spend 20 minutes giving you a real long problem. You know, I'll save that for the exam just so you can show me that you know what to do, right? So that was just supposed to be just a quick, easy polynomial. You know, I'm just trying to be real. I don't want to, you know, give you any false impressions as to, you know, that's the test question. It'll be that, but harder. The second question was just, again, to keep you on track with what we're going to be doing in class today. This is the last section we're going to cover before the test, which is on Tuesday. All right? So, yes? Just the slope, yeah, because again, time-wise, I didn't want to invest time to get the equation. So, yep. So that's another thing to pay attention to on the test. If I ask for just the slope, I mean, don't go doing all the equation stuff because I'm trying to save you time, right? If you went all the way, it's fine. All right, anything else over the quiz or anything else? Yes?
Up the whole time.
Was what up the whole time? Yes, it's been there this whole time. Yeah. Did you forget the limit formula?
I switched A and H on the top one. Like
You did
F of H plus A.
H plus A?
Yeah.
Oh, that'll work.
Oh, okay.
It'll still work. Yeah, because addition's commutative, so you should still get an answer that way. Okay, so today, what is today about? Well, there's a geometric approach to this, and then there's the algebra approach. And the algebra approach is really what you're going to be tested mostly on and what you need to be able to do. But it is good to get an idea geometrically of what's happening. So what we know up to this point is that if we're given a function, that we should be able to compute the slope of the tangent line anywhere on that function, so long as the limit that we use exists. And in the lecture video, there are 3 conditions where it would not exist. And I asked you for one of the 3. So they are, at a jump, anywhere you have a break in the graph, at that point you cannot have a derivative. A corner, anywhere you have a corner, a point where the graph comes up, you cannot have a derivative at that point. And then anywhere you have a vertical tangent. So we will talk about that later, all right? But let me draw a function right now that you can have a derivative at every point. So here's an example.
What if a function has a hole?
If it has a hole,
Yes. Like, let's say, for instance, let's say, for instance, it's just some polynomial in the very middle of it, it has a hole.
so at that hole, you're asking me about at the hole, okay? I'll answer that question with a very important theorem that was at the end of the notes. Where is it? Where the heck is it? I think it's right above this one, right there. Theorem 2.2.7 theorem, differentiability implies continuity. So if the function is differentiable at a point, right, then it must be continuous at that point. Right? That's what that says. If it's differentiable at a point, then it must be continuous. So let's just take what you're asking, for example, and you have a hole and you're asking about right here, right? Well, let's say that it is differentiable there, all right? Then that would mean that it has to be continuous there. But it's not continuous, right? So it turns out that if it's not continuous, then it can't be differentiable. I'll address that later when we get down to that part of the notes.
Whether that would just be a limit there, or that...
You could talk about the limit of the function, but you couldn't talk about a slope of a tangent line. You can't talk about the slope of a tangent line at a point that doesn't exist on the function.
Okay.
Right? That's the idea. Good question. All right, so if we are looking at a function, and I'm going to make one up here. Let's do this. Let's go up, back down through 0, back up like this. All right, so that's my function f. Everywhere on this function there is a tangent line, right? And the idea of this section was that if I just pick an x value, let's say here, and go up and just measure the slope of that tangent line, I could write down what that is as a number, right? That would be what, some positive number? Maybe, I don't know, 2, right? So let's say right here it would be 2. And then I could do that for every point, right? I would go to every point and write down a number at every point. And then on a separate graph, what I could do is for each point here, actually draw that number. So let's replace that with like -5. So -5 here, let's say the slope of that line is 2. So I come over here to -5, and I just plot the number 1, 2, 2 units up, right? And I do that for every single x value that's here. So I come over here and, well, what about here at -3, go up here, what's the slope of tangent line there? 0, so that means at -3, over here I plot it as 0. And I'm going to do that for every point. And what happens is if you connect all these points, you get a curve, don't you? And this curve is a new function. And that function, we call f prime, is the derivative of this function. So this is the first time that you've ever seen anything like this. What we have is a procedure called taking the derivative of a function, where it takes in a function, here it is, and we take the derivative of it and it spits out a function. This new function is called the derivative. Now, we've never seen anything like that before. What we've seen in the past is we have a function. We know functions take in numbers, spit out numbers, right? You can even plug functions into functions. Composition. College algebra, f of g of x, something like that. We know that functions can take in functions, spit out functions. But this is a completely different animal. This takes in a function and spits out a new function, all right? Things that do this are called, this is specifically called an operator, a functional operator. It operates on functions, takes it in, does something, and it spits it out, okay? So this should look brand new to you, all right? Because we're not doing algebra to it. It's not like we're squaring it or doubling it. No, we're differentiating the function to create a new function. So let's try and finish the graph of this. Let's see. I know that over here, anywhere to the left of -5, right, I've got positive slopes. And it appears that these slopes are getting more vertical, which means it's going to correspond to larger positive numbers. So on my graph to the left of -5 here, I should have positive numbers, but they should be bigger and bigger as I go out. So something like this. Do y'all see that? But as I start to move towards -3, these positive slopes start to get less steep, which means they're smaller positive numbers, but still positive, and they're heading towards 0. So between -5 and 3, positive numbers headed towards 0. And then I continue. Once I get past -3, all my slopes are going to be starting to pitch downward. So I have a very shallow pitch, so these are small negative numbers, until I get to here. That looks like maybe what, -1? And then once I get past that, doesn't it start to come back to 0? So I'm going to start at 0. I'm going to head to negative numbers until I get to -1, and then I'm going to come back to 0. That's what I've got to do between, let's call this 3. Between -3 and let's say 3, I've got to be negative numbers. I've got to go down to the lowest point is going to be -1. That doesn't look like -1. -1. I'm going to head down to -1. Still continuing negative numbers, but back up to 0. This is one of these topics in this class where it's, if you don't see it, it's like, what the hell is he drawing up there? And then once you see it, it's the light bulb effect, and you're like, got it, you know? So I'm waiting for everyone to have that light bulb moment. Hopefully it happens today, not a week or two from now. All right, so what's happening? We're back here, right? We're back right here. We had a slope of a tangent line that was 0. What's going to happen after I get past that and go to the right? Positive numbers, but they're going to get larger and larger. So over here on my graph, I should have positive numbers that get bigger and bigger and bigger. And that's it. That would be the graph. On your homework, there's a couple of problems where the book, they provide you some graphs and they ask you to draw them yourself. And it's a very loose drawing. I mean, you do your best, okay? It doesn't have to be perfect. And then there's another section where they give you a bunch of functions and then they give you a bunch of derivatives, graphs, and it's match. Match the function to its derivative. You think you can handle that? Should I do another one? Do one more? Okay. Oh, I should have pointed out, this looks like a polynomial function, right? The one that we had? Looks like a cubic, right? But it could also be a 5th degree or a 7th degree. But it looks like a cubic. Notice that the derivative looks like a quadratic, doesn't it? But this could also be a 4th degree or a 6th degree. And it does turn out that if you have a cubic function and you take its derivative, you will have a quadratic. If you take a quadratic, take its derivative, you'll have a linear function. So what happens is every time you take the derivative of a polynomial, the derivative is 1 degree less than where it started. But that, we're getting ahead of ourselves. I'm just pointing it out in the picture here.
If it was like x to the 10,
Mm-hmm.
and then we take the derivative, it'd be like x to the 9.
X to the 9th. And if you do another derivative,
Then it'd be to the 8.
and it would just keep going down. But that's only polynomials, and polynomials behave very well when it comes to differentiation. Okay, let me give you another one. M for math. Yay, math. No? All right. We have some issues here. There are 3 places where we will not be able to have a derivative because I have 3 corners. 1, 2, 3. I intentionally did not arc these around, curve them. I wanted them to be sharp corners. But let's talk about why it's going to be an issue. Let's try and graph its derivative over here. So talk to me about this point, this point, this point, this point, this point, all of the points on this little line segment from here to here. What can you tell me about the slope of the tangent line? They're positive, and they're always the same, right? Because it's a line, the slope at every one of these points is the same value. And it looks like it's about what? 1 or 2? Yeah, what do y'all want to say? I don't care.
1 or 2x.
1 or 2?
2.
Doesn't matter. Doesn't matter. It's 2. Let's do it. 2, right? So what we're going to do is everything to the left of this value. Now I haven't given you that value, so let me just throw it in here. How about -4 there? Let me say that this is +4 here, just to help us put everything on in the correct position. What I'm going to say is everything to the left of -4, right? The derivative of it should spit out what? 2, +2. So here's -4. And everything to the left, I'm going to be up here at 2, right? I put all these points up here, and really it would just create this little straight line like that.
At that point, would it have an open pole at both?
Yeah, I intentionally didn't do anything here because I wanted you to think about that. What's going to happen at -4? Well, to help us solve that question, let's talk about what's happening on the other side, okay? Bless you. How about if I take any of these points on this little line segment here? What about that slope? It's negative, and they're constant, right? It's always the same slope. So let's say -2, yeah? So anything between -4 to 0, I've got -2. So I'd be putting points down here, you know, here, 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 all these points, and I'd create another little line segment like that. Yeah, but at -4, right? At -4, your derivative does not exist. Okay, you cannot tell me that at the top of that peak, the slope is 2. You can't tell me at the top of the peak the slope is -2. It can't be both at the same time, right? And it's nothing in between, okay? It's not 0. It's not flat because there's the sharp corner. So what we do is we leave this as a open and an open like this. So this is what it takes for a derivative to not exist. When you look at the derivative, there's a break. Do you see that? You have some discontinuity in the derivative. Don't confuse what I'm saying. I'm not saying that this is discontinuous. This is a continuous function, right? I can draw it without picking up my pencil. But when I try and draw the derivative, I must pick up my pencil. So the derivative fails to be continuous, which means, at this point, -4, which means the original function fails to be differentiable at -4. What would happen if I moved to the right of 0? Same thing, +2 again. So I'm back up here at +2 to the left of 0 until I get to 4, right? And then it's going to jump back down to -2. And I can put open circles here, and I also need open circles there. And that is the derivative.
But that can't exist, right?
No, the derivative is defined everywhere except -4, 0, and 4. So this function is differentiable everywhere except those 3 points. Make sense? Yes.
So if they were curves at -4, 0, and 4,
Uh-huh.
derivative,
If these were curves,
Yeah.
like this,
then the line segments would kind of connect as
yes, they would. Yep, what would happen is, see, as we start to get closer to -4, I'm going to have to start pitching away down towards 0, right? So as I would be moving towards -4, I would have to start to go towards 0. I would go through it, and then I would have to come back, and then it would do the same thing. Oh, shit. It would go like this and like that, and then this one would curve. I'm going to miss it. There we go. That's what it would look like had those been curved. Yeah?
So algebraically, are these, how does that work at these poles?
You mean,
Are they like 0 over 0, or what's going on?
yeah, we're going to look at it, because the classic example for an example of a function that fails to be differentiable is the absolute value function. So what we're going to do is we're going to try and take the derivative of it at 0, at the corner, and we're going to see what happens. You'll see the algebra is going to fall apart. Okay? All right, so that's the geometric idea behind the derivative. And because we're starting with a function, f, and we're taking the derivative of it, I'm going to put a function f of x, like this. And we're getting something that's being spit out called the derivative. We can also look at this as a new function. And so what we're going to do today with the algebra side of it is we're going to make a slight tweak to the formulas that we had before. Right? The two formulas I said to hardwire, we're going to tweak it just a little bit. So here we go. I thought this is the way I would motivate the idea today. I'm going to motivate it with an example. So let's take the quiz problem. X squared minus 5x. And I asked you to find the slope, right? I said find the slope at the point 2, -6. That's what I wanted, right? And we know what we need to do for that, right? But I'm gonna modify this a little bit. I'm gonna say and at 1, well, what would I get when I plug in 1 there? 1, -4? And I want you to plug in 0. That's at 0, 0, right? And I'm getting kind of tired of plugging in these values, like to figure out what comes out. So I'm just going to give you what the x is. If I tell you what the x is, that's your a, isn't it? And that's enough, right? For you to figure out all the other stuff. So I want you to do it at there and at 4 something, whatever that is. Then at -4 something. And then I want you to do it at 10 something. I want you to do it at -10 something. Yeah, and so right now where we stand in the class is if I gave this to you, you would go and you would actually do each of these. And these would be all separate problems, wouldn't they? Yeah. This would be one problem, then another limit. And you don't want to do all that, do you? I don't either. So can we find a generalization that will allow us to just do the limit one time? Yes. And then from that, just be able to plug in and get the answers. And the answer is yes. Okay, so we are going to create a function that will do the slope of the tangent line for us, but it requires using the same limit we had before. So I'm going to write down one of the two versions. Remember, the slope of the tangent line is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. That was one of the two, right? And I told you not to get too comfortable, like don't lock yourself into one or the other, right? Always be flexible. But I think I did say that this one is the one we would use more often. And the reason why is this. The slope of the tangent line, when we said that, this meant at x equals a, right? That's the formula. If you go to the graph and you go to the point A, this right here will give you the slope of that line at A, and at A only. What I'm going to do, or what we're going to do, is we're going to say, look, we want to keep that A arbitrary. I don't want to lock it in at 2. I don't want to lock it in at 1 or 0 or 4 or negative. I don't want to lock it. I just want to leave it free to be a variable. So I'm going to replace this concept of x equaling A with the idea of, hey, let's just let x be itself, x. Let's just let x be x. Okay, so I'm saying, look, I'm not going to make that a constant. I'm just going to let it be a variable. And how does that formula change? Not much, right? That goes x and x right there. That's it, right? That's all that happens. So this formula becomes the limit, right? The limit as h approaches 0 of f of x plus h minus f of x all over h equals the slope of the tangent line, right? At where? At x. This is equal to f prime of x, which is called the derivative of f at x. We talked about what that meant last class. This meant the derivative of the function at x. And you can see by replacing the a with x, you can kind of see this is a new function of x, right? A new function. So let's do the problem that we did today. Let's get a general derivative of it. This is our general derivative. And then we can go answer all those questions very easily. Yes? Well, you want the slope of the tangent line, okay? The slope of the tangent line later on will guide us in trying to find maximums and minimums of functions just in general. Okay, so it's a tool that we are going to use to analyze function behavior later. If that's okay. Is that okay? All right. So let's do it. Find f prime of x for, let's do the quiz problem. F of x equals x squared minus 5x. Notice I'm not giving us a point, right? I'm not telling you where. This is going to be a general answer. Whatever we get should work for any x value that someone hands me. So I write it down. The derivative of f at x will be the limit as h goes to 0, f of x plus h minus f of x all over h. This is the limit as h goes to 0. And now we get to actually use the function itself, right? What was given to figure out what the top left corner is. So what do I get if I replace my x's here with x plus h? Okay, x plus h squared minus 5 times x plus h. Everyone agree? That's the top left corner. I'm going to subtract from that what? This, right? That's f of x. So I'm going to subtract this. So I'm going to subtract, in parentheses, the original function. And if you're comfortable distributing the negative through without writing the parentheses all in one line, that's okay with me. I just want to be clear for everyone that we are subtracting the entire function. Any questions on that? Okay? Now it's algebra time. I get to expand this. X plus h times x plus h.
You still haven't shown the past couple.
Yeah, we'll get to it. Next lecture we will, not this one. Okay, then I'm distributing -5 through. What am I hoping is going to happen?
Some of this stuff's gonna cancel.
Yeah, I'm gonna really hope that whatever I get up top, once I clean it up, everything that's left should have a what in it? An h, because I'm going to need this h on the bottom to go away. So distribute the -5 through, distribute the negative through. This is probably the biggest mistake I see in the history of me trying to help students learn Cal 1, is forgetting the distribution of that negative sign correctly, and then they never get things to cancel, and then it's all just a disaster after that. So you want everything that does not have an h to go away. If that doesn't happen, go back up and look at your work. Make sure that you did everything correctly. Can we put anything that's left together, any of these like terms? No, but I can factor an h out of all of them, right? So I'll do that on the next line, which I'll put right here. I'm going to factor an h out of the numerator. So that'll leave me with the h out here, a 2x here. What about here? Plus h, and then take an h out of this, I got -5. And then all of that over h. And there you're going to get your cancellation of your h's.
You have 2x minus 5.
These h's are going to go. Any questions? Now we'll let h go to 0. And I'm even going to write it one more time just to be thorough. Here's where I am. Limit h goes to 0. I have 2x plus h minus 5. That's the expression I have left, right? And I'm going to let h go away. And when that happens, I get 2x minus 5. That is the derivative of the function. Now, let's just look at something real quick. This original function was a quadratic, right? And I told you to recognize earlier that when we had that cubic looking thing, it looked like the derivative was quadratic. Here we have a quadratic. Its derivative is linear, which is kind of what I said would happen. And it does.
The derivative of the linear function, the derivative of the derivative, it would just be a constant.
Yes, the derivative of a linear function will be constant. This is a linear function. Go to any point on that line. What's the derivative? It's the same everywhere, right? So the derivative of any linear function should be a constant. In this case, well, in that case, it would be 2. Yeah. Okay. All right, so there it is, right? So we need to understand, we started with a function. We applied differentiation to it, and it created a new function. There it is. There's the new function. All right? Now, that function will spit out slopes of tangent lines for that function. All I have to do is provide what x you want me to go look at. So on the quiz, I wanted you to look at the point, 2, -6? What was the x coordinate that I provided here? 2. That's my x, right? Go to that formula and plug in x, or plug in 2. So here's how I'd write this. F prime at 2, right, that's the 2, I'm plugging in 2, is equal to 2 times 2 minus 5, which equals -1. That was the correct answer on the quiz. Now you got it by doing it different, but that's the correct answer. The advantage to this formula, though, is now if someone says, hey, what's the slope of the tangent at 1, -4, all I have to do is plug 1 into that. And that would be what? -3. And I can do this all day. Yes?
So
Yes, yes, you would, because, yeah, the only thing that this is doing for us is it's giving us a general answer. Now, if you want the equation of the tangent line at any of these, you've got the slopes, you go grab your points, and you can do equations for each one. This makes sense? Okay. Do you see the advantage of having a general answer? It allows you to knock out as many points as you want quickly without having to redo the limit every single time.
I can see how it would be very useful finding the global highest and lowest.
Yeah, so let's blow the doors off of this real quick. I think it's time to blow the doors open a little bit. You might like this a lot. You might not. I want us to find the derivative, okay, for this. I have to admit, I'm getting goosebumps because of what I'm about to do. But I just love math that much that this is really exciting to me. All right? Yes. Okay? You know where I'm headed with this, kind of? Okay. That's a quadratic function. That's a general quadratic function. That's the way they're presented to us in college algebra. Ax squared plus bx plus c. They tell us a, b, and c are numbers. They tell us a is not 0. Okay, so let's assume all that. That's just a general quadratic. Let's find the derivative of a general quadratic function. The derivative of a general quadratic function should be the limit as h goes to 0 of f of x plus h minus f of x over h. I must replace into my function x plus h everywhere I see an x, and then subtract from that this function itself. Here we go. Limit h goes to 0 of a times x plus h squared plus b times x plus h plus c. So that's the top left corner, right? Minus f of x. So I would do parentheses here, wouldn't I? I'm not going to. I'm going to just do the distribution mentally. It would change that to minus, that to minus, that to minus. So minus ax squared minus bx minus c, all of this over h. What's my next step? Do all the algebra, right? Expand everything out and hope to get everything that has an x, everything that doesn't have an h to go away. Limit h goes to 0 of, let's see, this right here is x squared plus 2xh plus h squared, but times a, right? So that a would pass through to each of those three terms. So I would have ax squared plus 2axh plus ah squared. Does anybody have a question on that? Then this plus bx plus bh plus c, then minus ax squared minus bx minus c all over h.
That's nice.
Yes, it is nice. ax squared gone. bx gone. c gone. Everything that's left has an h. Wonderful.
It's a linear.
Yeah. So this is now limit h goes to 0. All right, I'm going to factor an h out of each of those to save myself one step. When I pull an h out of this first one, I have 2ax plus ah plus b. Anything else? That's it. All over h. The h's will reduce out to be a 1. And now I'm free to let h go to 0. Go ahead and let h go to 0. You should get 2ax plus b. That is the slope. This will give you the slope of the tangent line at any point on the parabola. You give me x, I give you an answer, right? Now, you might be saying, well, what about the a's and b's? Well, someone would have had to have told me what a, b, and c were for me to be able to even start this, right? Like to graph this? All right. Quadratic linear, right? Quadratic linear. Now, this is the part that I thought would be kind of, hopefully, a little mind-blowing. Do you remember in college algebra that when you were being taught about parabolas, that you were told about this very important point? Yes. I'm going to draw two parabolas. These are not the same function, but the parabolas can open up or down, right? In either case, this point was called the vertex. And there were ways to get the vertex. One way was to complete the square, and it was a real disaster. But the other way was a formula. Do you remember the formula for the vertex? The vertex was, do you remember this? HK. We called it HK, yes? Do you remember them telling you that H was negative b over 2a? Do you remember that? Show of hands. How many of you remember the H coordinate? Okay.
And then you had to plug that in.
Then you plug it into the function to get k. But that's less relevant here. What's relevant is where this formula comes from. So take a look back at these parabolas. At the vertex, what can you tell me about its derivative?
0.
It's 0, right? At the vertex of a parabola, this should be 0, shouldn't it?
Yeah.
The derivative should be 0. The derivative should be 0. Let's walk over here and let's set that equal to 0. Set this equal to 0, everyone. What do you get? 2ax plus b equals 0. Subtract b on both sides, right? We're solving for x. X is negative b over 2a. The x coordinate that will provide you with the flat tangent line has got to be negative b over 2a. So we define it that way. Make sense?
So that's where they got the H.
That's where it comes from. They just call it h because it's the vertex. Isn't h the x coordinate of this point? What I said here was, look, where, at what x coordinate, right, where on this curve is the derivative 0? I said, well, shit, that's the derivative. So if I just set that to 0, that'll tell me what x coordinate this happens at. And lo and behold, it's negative b over 2a. So in college algebra, we just give you that. We say, hey, guess what? If you want to find that point, then that's all you have to do. All right.
Basically, when we were trying to find the vertex, we were trying to figure out what the derivative.
We wanted to know when the derivative was 0, but someone had already done that for us. And they gave us the shortcut. Yeah. Now, with this in mind, I'm going places I didn't plan on going today, sorry. But this is good stuff right here, I think. Okay, so in college algebra, we were never really trying to deal with this situation. This would be a general cubic function, wouldn't it? And we did graph cubic functions in college algebra. But nobody ever, we were told it could do something like that, right? Or it might do something like this. And we didn't know how many humps there would be. We'd have to analyze a little more, but we never, ever tried to find these points, did we? We never did. Well, guess what? We can now, because if I take the derivative of this, right, I will get a function. That function will be quadratic. And because it's quadratic, it should have no solutions, one solution, or two solutions. Those are the only possibilities, right? So once I actually do it, I will be able to attain where those are happening. I would have to take the derivative, get a quadratic function, set it equal to 0, and then go solve. What if it's 4th degree? Derivative would be 3rd degree. Now we're going to start to run into some problems, right? Because we don't have a general formula for solving third degree equations. Pardon? The derivative of the derivative, actually it won't work that way, unfortunately.
The derivative and then set that as 0?
Yes. If this were fourth degree, what I'm saying is if this was fourth degree, the derivative would be third degree. If you set a third degree equal to 0, there's not a clean formula for it. There is a formula, by the way. You know, we all know the quadratic formula, right? Like, but if it's third degree, there is a formula, but it's pretty big and ugly. There's a fourth degree formula, and I'll have to go back and look, but I believe it's fifth degree. There's not a fifth degree, and there actually does not exist one. It's been proven it is impossible to have a fifth degree equation and higher. So it's not, I'm not saying that we just haven't found it. There's a proof that shows it can't exist. So the only hope we ever have for solving equations, polynomial equations, are quadratics, third degree, and fourth degree. Anything else we do is going to have to be either pure luck or a computer to get us to the solutions. We will not. We will have a method for it, though. And guess what? The method will involve derivatives. Yeah. Okay. I have gone way, way, way out there. I want to do some more examples. Are y'all feeling okay? Don't you feel good now that you know where negative b over 2a came from? That should just make you feel good inside. No? Just me. Okay, that's fine. Find f prime of t, where f of t equals t plus 1 over 2t minus 1. Now, I've changed the variable around here to t, just because we need to be comfortable with the idea that x is a dummy variable, and we can always replace x with any other letter. T is one that we like to use.
We still have to use the f of a one. The f h code is...
Yes.
We still have to
Yes.
Okay.
We are, look, from 2.2 and on, we are pretty much going to stick to the limit h goes to 0 formula exclusively. Remember, there was 2 last class. We're going to stick exclusively to the h goes to 0, 1. But only until the next time we meet, because the next time we meet, I'm going to show you that there's a way to do derivatives without limits. Shortcuts. Super shortcuts. And that's where I said, I think I may have told you you're going to be upset with me. Some of you have already seen calculus. Okay, I know that for a fact. So let's do a little spoiler here. We just did that function, right? And we found that the derivative was this, right? Okay, so super shortcut is what you do is you look at this polynomial, you write the powers of the x down. What you do is you take that power and you drop it out front, and you reduce that power by 1. Take this power, drop it out front, reduce this power by 1. If I reduce this by 1, what does it become? X to the 0, x to the 0 is 1. So this will become a 2 x to the first power minus 5 times 1. That's it.
Oh, really?
Yes. Pardon?
I saw it earlier.
Yes. If you've seen calculus, you know that there's a big cake with a cherry on top coming. But the problem is that you must understand the limit. You must suffer through the limit first to have an appreciation for the shortcuts. All right? And look, that's what distinguishes a calculus class from a business calculus class. In a business calculus class, it's a very short introduction to limits, very short. And that's it. And then they go right to here are all the shortcuts. What makes Cal 1 is that you must get into the limits, you must get your hands dirty with the limits, you must be able to take derivatives with limits, and then we hand you the formulas. And you're like all happy, and then I tell you, but guess what? The trade-off is that you get the formulas, but now the functions get harder. Okay, so instead of dealing with a little polynomial, I'm going to be putting like sines combined with roots, combined with rational functions, all mixed in together. And now go find the derivative with all your little shortcuts that you were happy to find, like happy to have. So it's just, I mean, it's a give and a take, all right? But it will be a way we can check our answers pretty easily. All right, let's do this one. Limit, okay, I'm going to write f prime of t equals the limit as h goes to 0 of f of t plus h minus f of t all over h. So that's the same formula, just replacing the x's with t's. And then I go and I plug in, right? I go to this function and I say I'm going to replace this t with t plus h, this t with t plus h. Limit h goes to 0. All right. T plus h plus 1 over 2 times t plus h minus 1.
Over H.
Don't forget this part. That's just top left corner, right? Minus
Double equation.
f of t, which is everything we see there, minus t plus 1 over 2t minus 1. Now all of this over h. The advantage that we had in last class was that this second piece right here was always a number, wasn't it? Like we always just plugged in and got a number here. Now that we're generalizing, that top right piece is never going to be a number. It's always going to be another function, which is always going to make this a little bit more challenging algebraically. But in the famous words of one of my ex-girlfriends, that is life, right? That's the way shit goes, right? Sometimes.
You sure that wasn't your wife that said that?
Fortunately, not yet. All right, so here we go.
Okay, whatever.
Common denominator. I moved the limit out. You see why I gave myself some space? Because I'm about to make a common denominator.
Just multiply the bottom to the right.
Yeah, just take this, slap this up here, take this, slap this here and here, and that's it. And then we'll have to multiply, and it's, you know, you're guaranteed ugliness here. So here comes my 2t minus 1, and then 2t plus h minus 1, 2t plus h minus 1.
That's the bottom you're not messing with.
Pardon?
What is the bottom you're not messing with?
Yeah, the bottom, this has been the theme the whole way through since we've been doing limits, is when you get common denominators, don't try and figure out what the bottom is going to be. Just put them side by side and be done. Any questions there? Yes? Where's that? Oh, I'm not doing a conjugate. Is that what you're thinking? Conjugate? No? Oh, here? Because, okay, because this subtraction, I'm leaving it. I'm not distributing it through. If I did, I would change that to a minus, and this would now become a plus. But I'm leaving it. Just remember, it's like a fraction. If you have negative 3/4, you can write negative 3/4, or you can write negative 3 on top over 4, or you can write 3 over negative 4. This version, we're just kind of leaving it out and messing with this. That's what I'm doing here. I'm just leaving it here. If this were a polynomial, I would pass it through, but it's not. It's a rational function, so I'm choosing not to mess with it. I will have to do it, just not yet. All right. Wow. All right. Well, this is where the algebra comes in. You know what I'll do? I'll do this. 2t minus 1 times t plus h plus 1. I'm just rewriting that. Minus t plus 1 and then times this one, right? I think on this one I will distribute the 2 through. Because on my next step I have to put those both together, don't I? So I'm going to put 2t plus 2h minus 1. Be careful, the 2 only goes to those two. It doesn't have an effect on that one. That's my new numerator all over the common denominator, which is 2t minus 1, then times, again, I'll put that through, 2t plus 2h minus 1. That's my common. That's what they both had. And then all of that over h. And what am I looking to have happen here?
Some sort of H.
Some h go away, right? Can I erase the top two lines? Leave this one? All right. Equals limit. H goes to 0. All right, here we go. Start to distribute. 2t times t, 2t times h, 2t times 1. After I do that, -1, -1, -1, do all that, right? And then I got to do the same thing over there. And then I got to pass a negative sign through. So I should get, here we go, 2t squared. That's this. Help me out.
Minus 2th.
Plus 2t.
Plus 2th plus 2t minus t minus h minus, I think I forgot to put t. Didn't you say minus t? Minus h minus 1. Okay, so that's the first multiplication. That's all this.
Minus parentheses.
Yeah, this one, what I think I'll do is I'll do this. That's going to be what? 2t squared, but I'm going to have to subtract that. So minus 2t squared. Then I'm going to do this 2th minus it though. Here to here, minus t, but minus it, so plus t. Then 1 goes through. So minus 2t minus 2h plus 1. All over the common denominator. I don't like the way that 1 came out over here. 1, okay, and then all over the common denominator, 2t minus 1 times 2t plus 2h minus 1. All of this over lowly little h there.
Write the whole line. Can I just put it like small line over h?
Put a small line over h? That's a good question. What do y'all think? Can I do this?
Because that's what I was doing. I didn't want to.
That's technically not correct. No, it's not. Yeah, the notation's not correct. So I'll give you an example. If I write 12 divided by 3 divided by 4, if I don't give you any indication as to which of these division bars is bigger, is this 12 over 3 first, then divided by 4? Or is this 3 over 4 first, then divided by 12? Because it's not going to give you the same answer, right? Do that first, you get what? 4, right? Get 4 there, and now divide by 4, you get 1. But now do these two first. 3/4, 0.75. Divide 12 by 0.75, it's going to be bigger than 12. So which is it, 1 or, it's bad notation is what it is. So I would have to actually say this right here would mean do that first, then come in with the 4. So if you do a shorter one here, what you're saying is that this must be done before that one. And you wouldn't be able to write this like this and flip. It wouldn't work. So you have to have this be a long division bar. Good question, very good question. Those are those little subtle things that somehow get lost in our education, like how important something like that is. All right, did a bunch of stuff cancel? 2t squared, 2t squared. I'm looking for everything that doesn't have -1, +1. Oh, wait, these go too. Wow, I got lucky. I didn't even need that to happen, right? Because they both had h's, but they went away.
You just got left with the.
I just have -3h. That's it. Okay, awesome. See, that one's so bad. Limit. Remember, I'm just the messenger, okay? I'm just here to deliver the product. I didn't make this up, okay? You can thank Isaac Newton.
It's kind of crazy that he thought all of this up back in his day.
He and Gottfried Leibniz, right? I talk about that in the video.
Together, or is it like total
Totally independent, had no knowledge of each other's existence. Pretty amazing. We're talking about the two fathers of calculus, the two people who developed calculus independently of each other. All right, this is beautiful because the h's are gone now, right? I could do that 1 over h or h over 1 and flip it, but I'm hoping everyone's comfortable now with that. And you no longer have division by 0. And so you can let h go to 0. Let's do it. Up top, I still have what? -3 over, notice no more limit, right? Okay. 2t minus 1. And then this is gone. So another 2t minus 1. So it's 2t minus 1 squared on the bottom. So our answer is -3 over 2t minus 1 squared. 2t minus 1 that quantity squared.
We can leave it like that, or do you want us to go ahead and?
That's it. Nope. Nope. That's it. Yes.
So why did you cross out
The 2h
on your
up here.
No, down there, because it went to 0.
Oh yeah, because when I take the limit now, this goes to 0. It's gone, and all you're left with is a 2t minus 1. I should technically have written it down again and just wrote it as -3 over that, and then let h go to 0. But it's trying to save some time.
So when you plug that one into the calculator, you get like a. So this one you get the asymptotes or whatever. Why is that?
Ooh. Well, I think what we would need to do is just graph them. If you wanted to really like see the two of them together, we could. I don't mind doing it. Let me do it this way. You want to erase the board? No? So if someone erases the board, I'll graph them. Bonus points? Oh, no, just kidding. Everyone's going to stampede up to the board. That's all right. I'll graph them. Someone can decide if they want to do that. Okay, so the original function was t plus 1 over 2t minus 1. And then the other one was, our answer was -3. -3 over 2t minus 1, that quantity squared. Uh-oh. Ah. All right. The red one is the original function. The black one is its derivative. Okay? So let's go along the red function. Tell me about the slope of the tangent line. It's really close to 0, but it's slightly pitched down, right? So it should be a very small negative number. And notice that the black curve is asymptotically approaching 0, but it's from below. So it's a very small negative number. And then still small negative, still small negative. Now watch what happens. Start to get big negative, right? And so the slope is going big negative. And it just kind of follows it down, big negative number, down to negative infinity, because this is trying to become vertical. Then on the other side, it's similar. Is this what you're asking? Yes? So look, here, if we're anywhere on this curve, do you agree anywhere on this curve, the slope is negative? Yes? Anywhere. So that's why the derivative is always negative. It's below the x-axis. It's just a matter of how negative. So over here, I've got almost like straight, but that's negative infinity, basically. And then as I go here, I start to get less negative, start to almost flatten out to 0, but not quite. Good? All right. I always leave my mouse over there. The real challenge for you now is to be able to do enough of a variety of problems to get used to the algebra that's going to be required here. So there's a set of homework problems. Some of them are